Hi, everyone. Welcome to the 18th lecture of CS 188. Two announcements today. The Project 2 mini contest results are ready for presentation. I'll present them right after the break in today's lecture. And you have one thing to work on momentarily, which is homework 8, which has always consists of 3 parts: self-assessment of the previous one, then a written and an electronic, and that's due on Monday. Any questions about logistics? Okay, today's topic is hidden Markov models, possibly the most frequently used BaseNet model. Actually, before we do the math, let's look at a quick demo. So, this is what the Pacman world in your project 4 will look like. So, what we got here, we got Pacman in the top left corner. We got what looks like an empty board, but actually there's ghosts on there, but they're invisible. And Pacman is more powerful than you're used to in this project. Pacman can blast the ghost whenever they're on the same square. So Pacman wins out, and the goal is to find the ghost, track him down, and take him out. Put him into ghost jail, which is the bottom left. So how to do this? Well, you could start running around. This is just me playing with a keyboard. And the bottom right, you see 4 numbers, hop, up, and down. And those are the distances to the different ghosts. So there's 4 ghosts, and there's different distances to the different ghosts. And these ghosts are actually moving around. So let's see. Moving closer to blue ghost. We're very close to blue ghost. Sometimes 0, but we still didn't eat it somehow. Let's see if we can find another ghost. So it's pretty hard to find these ghosts when you can't see them, and all you have is distance measurements. But if you manage to run into one of them, you would actually get points. Oh, we ran into the cyan-colored ghost. Actually, they ran into us, and this gave us a ghost in jail, which gives us points. Let's see if another one wants to run into us. You should try to help them, of course, with your program, not just sit still. Oh, where's the orange one? Looks like we're getting closer. It's not that easy a game to play, just looking at these numbers. And that's kind of the motivation for today's lecture. If you have access to these numbers that were shown at the bottom here, can you do a calculation that makes it possible to... Oh, another one got themselves eaten. These are not the smartest ghosts. If you have access to those numbers, can you do something better than this poor play I've been doing here by maybe somehow extracting information about where the ghosts are most likely and then move towards that? And that's what HMM tools will give us. Of course, it's not just for tracking down ghosts. We'll see other applications for HMMs. So this will be all probabilistic reasoning. So quick probability recap. What is conditional probability, which will be key here? Conditional probability is, in this case, conditional of x given y is the probability that x and y are both taking on the values x, y divided by the probability of y. So the fraction of the time we have small x among the times that we have small y. Product rule is rearranging this and allows us to compose a joint distribution from a marginal and a conditional. The chain rule is repeated application of this, essentially the same thing. You can do this in any ordering of your choice for n variable, n factorial choices of expanding the chain rule. And x and y are independent if and only if, for all values x and y can take on, the probability of x and y is equal to the probability of x times the probability of y. And then conditional independence is the same idea. But in conditional independence, instead of having just x and y, there's also a z, and you just condition everywhere on z. And that's generally true in these equalities that we have for probabilities. If you have something that's true, in this case for x and y, you can just condition on z everywhere, and it'll still be true. And that's exactly what we did here. X and y are conditionally independent given z, if this condition holds true for all values of x, y, and z. And this is our notation for conditional independence. So we covered a lot of that in the context of Bayes nets, and today we're going to see a special kind of Bayes net that sees a particularly large amount of use compared to most Bayes nets. Okay, what we want to do is reason about sequences of observations. Where might this pop up in the real world? Let's say speech recognition. In speech recognition, you get a sequence of numbers coming in corresponding to the pressure of the air at that time. And you're supposed to decode that into a sentence or something. In remote localization, you have a robot going around a building, but even though we can see where the robot is, for the robot itself to know where it is, it needs to use some sensory information. That sensory information will not be perfect. It might have sensory information from maybe a camera looking around, or from a LiDAR, which is a laser beam you send out, and then it bounces back at you if you're lucky, and then you measure how long it took before it got back to you, and then you multiply that with the speed of light, and then based on that, you know how far away that obstacle is. You need a really good timer, obviously, because speed of light is very, very fast, but that's actually used quite often. User attention. As the user is navigating your website and goes to another website, what do you expect them to do? What might they be caring about on your website? Medical monitoring. Let's say you have a patient in an intensive care unit. You're measuring a lot of signals. Can you, from that, infer, from the aggregate of signals you've seen so far, infer if there's any emergency you should call in a physician, or whether you can just leave them alone and let them rest? So it's all about aggregating signals from the past into drawing a conclusion about what situation you are in right now. So we'll need to introduce time or space into our models. So here's a Bayes net in which we have time indexed variables. So x is the state of a system. xi is the state of the system at time I. We've seen this before. In Markov decision processes, we had a state, we called it S. It's called X now, but essentially it's the same thing. We have a state of the world, and it can vary over time, be different at every time step. It can also stay the same. What we have here also is actually this here is a Bayes net, where there's a conditional probability distribution for x2 given x1, a distribution for x3 given x2, and so forth. And what's special about these models, that the parameters we'll use will be tied, meaning that we'll have a generic distribution for xt given xt minus 1 that is the same for every time step. This was actually also true in our MDP models. It was always the same transition model. We're going to make the same assumption here. And so even though this Bayes net could in principle be infinitely long, the number of parameters is bounded. It's actually not that many. There is just two tables. One table for the conditional, and one table for the initial distribution. Okay, so these parameters here are called transition probabilities or dynamics, and specify how the state evolves over time. And then these are the initial state probabilities. Stationarity assumption is that the transition probabilities stay the same at all times. If somebody says we have a non-stationary process, then you'll need a different transition model for every time. So same as MDPs, but what's missing is actions. We're not going to worry about actions. They're not going to be present in this lecture. Okay, so what are some conditional independencies implied by this Bayes net? Well, past and the future are independent given the present. Like when we know this variable, let's call this the present, time t. Then once we know that variable, knowing something about the future does not tell us anything about the past, and other way around. We can calculate that with d-separation, or we can just intuitively conclude that. Each time step only depends on the previous. To predict what happens at the next time, just knowing the current time is the best thing you can know to predict that. Knowing more things about the past is not going to help you. This is called a first-order Markov property. You might say, well, what if it doesn't apply in my situation? What if in my situation, the state at the next time depends on the state at the current time and the state at the previous time? Well, to still be able to fit it in this format and to really fit the notion of what actually it means to be a state, you should then combine the state of the current time and the state of the previous time in one bigger state variable that you now call your state, and then you can use this model again. Because now this bigger state, which includes current state and previous time step state in your original formulation together, is enough to predict next state. Predict here could be probabilistic, of course. So really what this is just a base net that you can keep growing. And as time goes by, you keep growing it to keep up with time passing. Or as you traverse space, you keep growing it to keep up with the amount of space you have traversed. If we want to do any probabilistic reasoning in this base net, what we can do is we can just say, okay, we'll look at everything up to the current time or up to the time we care about, cap it off, and then we can run our standard base net inference algorithms. We can do variable elimination, we can do sampling, and so forth. But we'll see in this lecture and next lecture is some variations of those algorithms that are kind of easy to derive from first principles for Markov models, and that have equivalents as simplifications of the sampling and variable elimination algorithms you've already seen. Okay, let's look at an example Markov chain. Here we have a state space with two possible values the state can take on. It can be rainy or sunny. And maybe we observe this on a daily basis. So Monday, sunny, Tuesday, sunny, Wednesday, rainy, Thursday, rainy, and so forth. So our initial distribution is going to say it's sunny on the first time slice. And our conditional probability table, our dynamics model, is given by this table over here, saying that when it's sunny, there is a 90% chance it's sunny again the next day. When it's rainy, there is a 70% chance it's rainy again the next day, and then the complementary probability of being sunny. All right, so now we can start doing some calculations with this, but also let's look at a few other visualizations. So this is one way to look at it. That's rolling out the Markov model. Another way to represent the conditional probability table is to look at it in this format. So this looks like a finite state automaton. There is two possible values the state can be. So you have rain or sun, and then there is transition probabilities associated with each possible transition. So that's a pretty valid way to think of a Markov model. Another way to represent it and keep time a little more explicit in it is do essentially the same thing, but unroll one step when you draw this thing. Because when you go from sun to rain, it's really at the next time it'll be rainy. And so this model on the right makes that a little more explicit, that you progress in time. Okay, any questions about the formalism? Then let's do some calculations. So let's say the initial distribution is all probability on sun. What is the distribution after one time step? So let's see. Let's think about this. We have the initial distribution. We have a dynamics model for next state given current state. So we should be able to combine both of those to get the distribution at the next time step. Okay, probability of it being sunny at the next time step is the probability of it could initially be sunny or rainy. When it's sunny, then we need a transition from sun to sun. When it's rainy, we need a transition from rain to sun. That's our generic update equation to go from a distribution at time 1 to a distribution at time 2. In this particular case, initially we put a probability of 1 on sun, so only this first term here will have a non-zero contribution. And it'll be, in this case, transition model was 90% chance of staying sunny. We knew it was sunny at time 1, so we have 0.9 times 1 gives us 0.9. Okay, so what's the probability for x taking on a certain value on some time t in the further future? Well, what we just did, we can actually repeat that process quite easily, because it gave us the distribution at time 2. And going from 2 to 3 is the same calculation as going from 1 to 2. So we can just iterate the same calculation over and over to progress over time. writing this out on the slides, we know distribution at time 1. Then for time t, well, we say we can compute it recursively based on the distribution at time t minus 1, which is this summation over here, the sum over all possible values we could have at time t minus 1, jointly with xt. This itself we don't have available, but we have a conditional of xt given xt minus 1, and we'll recursively assume we have xt minus 1 distribution. So that gives us this expression over here. And this is an expression we can apply for each time slice to propagate forward to any time we care about. And this here, with forward simulation, that's referring to the model that we have available to model how the dynamics works in this world. Okay, so that now means we can run things forward in time. If we have a distribution at the initial time, we can use this update equation here to get the distribution at the next time. If you think about it, what is actually going on here, think about the Markov model. You have x1, x2. It's a BaseNet with 2 variables. You have all the distributions, all the tables. You have instantiated a distribution for the initial time for x1. And now you're running variable elimination to get the distribution for x2. So you're trying to compute p of x2 in this BaseNet. If you do that with variable elimination, you'll get the exact same expression shown here. Will not be any different, but this is such a simple situation, it's easier to just redrive it from scratch than to go through the very general framework and then finally arrive here. Okay, so let's do this. Let's say initially it's sunny. We've observed it, so all probability mass is on sun. We can propagate forward in our model. We already did that for one time step, became 0.9, 0.1. What if we propagate forward again? Same calculation. We end up with 0.84, 0.16. We can keep repeating this. And if we keep running this forever, if we had the patience, but if we run it long enough, we already see the pattern occurring, we'll converge onto 0.75, 0.25. This might remind you of something we've done before also. In value iteration, in policy evaluation, we had an update equation. It was then for the values. Now it's for the distribution over states. And if you repeated that update equation infinitely often, it would converge to a stationary point. Okay, what about if initially we observe it's raining? So we start from 0 and 1. We can follow the same update equation. We now get 0.3, 0.7. And we can repeat this process over and over and over and see what happens. We actually end up with the same distribution at time t equal infinity. So just like value iteration, policy evaluation, it doesn't matter how you initialize your values. There it was because it decays over time because of the discount factor. Here it's a slightly different effect, which we'll discuss in a little bit. But intuitively, it's the notion that if there is some randomness in the next day's weather, over time, the information about the weather on the first day will be erased because it will not affect anymore what you expect to happen. Let's say I ask you today, what's the weather going to be like in the year, 3000? You will not be basing that on exactly what the weather is like today. That will not affect your decision on what the weather will be like in the year 3000. It's too far out, and the transition model will dominate, not the initial distribution. You can do this with anything. You can have any initial distribution, and if you do the calculation with that transition model, you'll find you converge onto the same distribution, 0.75, 0.25. Of course, the specific numbers here are specific to the fact that we have the conditional probability tables shown early on here. This conditional probability table is what results in that particular stationary distribution. Okay, let's take a look at this in action. I think you've seen this grid in the value of perfect information lecture. So what are these numbers? They are the probabilities of the ghost being in that particular spot. There's only one ghost in this case. Let's first find this ghost by doing a few measurements. Where is the ghost? Somewhere here, it seems. It's pretty high probability. Okay, now, this button here, we're not going to worry about busting the ghost in this lecture. This button here, time plus 1, will make time progress. The ghost is moving randomly in this dynamics model. So equal probability moving to any neighboring square. So if we make time pass, what do we expect to happen? We expect the probability mass to spread out from being all concentrated here to neighboring squares. So let's see if that happens. Indeed, probability mass is kind of sifting out, so the ghost stays in place with a high probability and then sometimes randomly moves off to a neighboring square. If we let time pass again, the probability mass will diffuse more and more and ultimately diffuse back out over the entire board that we have here. We play this long enough. Takes a while though, a lot of clicking. We play this long enough, what we'll see is that we'll hit a stationary distribution where this doesn't change anymore. And it doesn't matter where we started, the distribution will be the same. What do we expect? It'll go back to the uniform distribution where everything is the same probability. It's starting to get closer, but this will require a lot more clicks before it gets all the way out there. Infinity, in this case, is not super close to us. But we're getting there, at least with most of the probability mass largely spread out and only very little left on the initial square. Okay, so that's the process of probability mass diffusing as time passes by. Now, this becomes more interesting when we have more interesting dynamics. So here we have circular dynamics, which means the ghosts will be going around in a circle. So what do you expect to happen when I press time plus 1? I see some no nods, because actually nothing's going to happen. These numbers are going to stay the same. Because if the ghost moves around in a circle, well, all that mass will just shift around and fall right back into place. So time plus 1, time plus 1, time plus 1, we're on the stationary distribution already for this circular motion, and so as time passes, nothing changes. We hit the stationary distribution from the beginning. Now if we go find the ghost, to change this distribution a little bit, let's see, somewhere here. Okay, we got some pretty high probability here for the ghost. If now we let time pass, what do we expect to happen? We expect that high probability to move around in a circle. Actually, for you guys, it'll move around in a circle this way. Let's see if that indeed happens. So there's the ghost moving around in a circle. I mean, that's our estimate of where the ghost is. The ghost doesn't need to be here at the reddest square. We think 50% chance the ghost is there. And our probability mass keeps following along with what we expect to happen, but at the same time diffusing because there's some probability the ghost moves randomly off to the side instead of following the circular pattern. And what do we expect to happen if we keep pushing the time plus 1 button? As more and more time passes, we'll go back to the stationary distribution where every square has a probability of 0.2. And again, this might require more clicks than we have patience for, but we see it's already getting pretty close, just a few rounds into what would be a full circle around. And right now, we have no idea where the ghost is. The probability mass is largely diffused over the entire board. What's another example of a distribution or a dynamics model? In this one, it's a whirlpool. So the ghost spins to the center. Wherever you start, you kind of spin around, but towards the center. So what happens if I just do time plus 1 here? This is not the stationary distribution, because you're inclined to spin to the center. So no matter where you are, a bunch of probability mass is going to shift around that circle and towards the center. So as I keep pushing time plus 1, here actually, without even measuring anything, because the stationary distribution is fairly concentrated to those two squares, we actually find out where the ghost is by just letting time pass and doing the appropriate calculation. Say, okay, it looks like the ghost is either here or there. We can go check, measure where the ghost actually is. It doesn't look like the ghost ended up there just yet, but it's maybe pretty close. So we now have observed the ghost is most likely here. We'll let time pass. What do you expect to happen? It'll go back to, we'll see it circle around while drifting towards the center. And Once it's in the center, it hops back and forth between those two squares. That's just how the whirlpool dynamics work in this world. So we've seen a few different world dynamics here. The first one was just randomly moving to a neighboring square. The stationary distribution was uniform over all the squares, as we saw. Then we saw the going around in a circle, where also the stationary distribution was uniform, and then and a little bit of noise was in there. And then this one here, it's drifting to the middle, and the stationary distribution is then putting probability mass mostly in the middle. So usually when time passes, we lose information about where the ghost might be, but for very specific dynamics where things converge together automatically, you can just let time pass and learn about where the ghost is. Any questions about this? Yes?
For the Ghostbusters, should all of the probabilities sum up to 1? Because there is only one ghost.
There's only one ghost. Yeah, these probabilities should always sum up to 1. Not sure if you were doing all the calculations in your head while these were flashing by. It's possible that they didn't always perfectly sum to 1 because of rounding errors showing only a small number of digits. But under the hood, they will sum to 1 if you show them in full precision. Okay, let's think a bit more about stationary distributions. For most chains, the influence of the initial distribution gets less and less over time. And so the distribution we end up with is independent of how you started out. There are exceptions to this. You can carefully design exceptions to this, but the most common case that you'll encounter, and if you just randomly put some transition model in place by randomly choosing numbers, this is what will happen. The stationary distribution is the distribution you hit at that point. The stationary distribution is one where if you apply the transition model, nothing changes. So actually, rather than applying the transition model infinitely often to understand what is now the stationary distribution, you can also just set up an equation. You can say the distribution at time infinity plus 1 has to be equal to the distribution at time infinity. That's what it means to be stationary, which is the infinite time stationary distribution. This is the update equation, and so we can solve this system of equations here to directly solve for the stationary distribution. It's just linear equations, because the transition model here, is known, is the p infinity of x, that's unknown. Those are the unknown variables. You might say, isn't 0 a solution? Yeah, so you need to find a solution to this linear system of equation that is not the solution that makes everything 0. You need to find this. There's actually infinitely many solutions to this equation, but there will typically be only one solution where all entries sum to 1. And that's the solution you want to find. So you want to solve this linear system in addition to sum over x, p infinity x equals 1. If you add this equation to the system of linear equations we already have there, then there will be most typically a unique solution, which is your stationary distribution. This should actually remind you of something we saw when we covered Markov decision processes and we looked at policy evaluation. In policy evaluation, we saw you can iterate the value iteration equations where you remove the max and you just choose the action based on the policy, and that gives you the value of that policy for each state. Or you could realize that once you remove the max, this is just a linear system of equations and just solve the linear system of equations directly to evaluate the value of a policy at each state. Same thing here. We could either iterate, which would be likely a lot of work, like if we asked you in an exam, find a stationary distribution. If you iterate, you're going to be busy for a long time. And you might not have time to solve some other questions. But if you use this equation, you say, I just need to solve this linear system of equations, and if we ask you to do that, it'll probably be a linear system that's very easy to solve, then you could just solve that linear system of equations, have the solution, and be done. Okay, let's look at some examples. And let's use the linear system of equations to find the stationary distribution of the rain, sunny Markov model. Okay, this is the two equations that say the distribution at time infinity should be the same after one update. The equations, the right-hand sides are what happens with one time update. Okay, so the unknowns are these guys here. A lot of them are the same. There's not 6 separate unknowns. There's only 2 unknowns here. P infinity of rain, P infinity of sun. The other 4 entries, which I'm drawing lines underneath, those are just numbers that we can take from this table over here. Let's fill them out. Now, let's solve the system of equations. Do a little bit of work. We get this here. Actually, we see that both of those equations tell us the same thing. It's really only one equation, but also we have that they need to sum to 1, and that gives us the solution. Summing to 1, and 1 has to be 3 times the other one, then it's going to be 0.75 and 0.25, which is our solution. Any questions about how this was done? Yes? There will always be at least one solution. It is not guaranteed that there is a unique solution. And so, let's think about this. How could we end up with a non-unique solution? Let's think about the iteration case, right? Let's imagine your initial state could be either in Wheeler or in Soda Hole. And let's say your dynamics model is such that when you're in Soda, you cannot leave Soda, and when you're in Wheeler, you cannot leave Wheeler. Then all of a sudden, your initial state will determine the stationary distribution you get at the end of doing infinite repetition. And when you solve the linear system of equations corresponding to this kind of transition model, you will find that it has 2 solutions instead of 1. I mean, it could be more. It could be that maybe if you're dropped in Soda Hole, if you're on 4th floor, you always end up staying on the 4th floor. You can't exit, and same for 1, 2, 3, 5, 6, and 7. And if that were the case, then you'd have 7 stationary distributions in Soda Hole, which you hit depending on where you started, and then 1 for Wheeler. So if you keep things separated like that they don't, essentially if there's 0 transition probabilities between certain regions of the state space, you can end up with multiple stationary distributions. Once you introduce a non-zero probability of transitioning between any pair of states, then typically end up with a single solution. There is another funny case, and I mean, these things are not too important for one idiot, but just because you ask, another funny case is where, let's say, you have a system where maybe you could either be in front of the classroom or you could be sitting in a chair in the classroom. And your transition model is, at the next time, if you're sitting, you're in front, and if you're in front, you're sitting. And you always go back and forth. Then you will not hit a stationary distribution either, because the dynamics is such that you always swap. So you will, if you start here, you'll end up there. If you start there, you'll end up here. And so you don't get this kind of convergence. And so whenever these special cases happen, is because there's a lot of zeros in the transitions between states, and so things don't get to naturally diffuse. Once there's some natural diffusion, then you get a single stationary distribution. Any other questions? Okay, let's think about where these Markov models might have already helped you in your life. Who here has used Google before? Who has not used Google before? Anybody? Curious. Everybody's used Google before. Okay, that's cool. So you guys are so young, you probably don't remember the time, you were not alive before Google existed. I was alive before Google existed. Google came into existence in 98, and before Google existed, it was very hard to find anything on the internet. And people used to bookmark things because it's so hard to find something. And so there were some search engines, but they didn't work all that well. And then you might have to scroll down to like the 100th option they returned, and then definitely bookmarking, so you don't want to do that again. Google really changed that. What was the key idea that they came up with at the time? The idea of PageRank. So, PageRank is a number assigned to each node in the web graph. So for every website, there is a rank number. And so Google came up with a rank number for every website. And so when you were to search something, in previous search engines, you would search, and it would then either just return websites that have matching words, but not know which websites are more interesting, or somebody would manually curate and say, I think this website is more important than this website, so if there's multiple websites with the correct word, let's show this one over that one. So I would do a manual page rank, which is really hard to do, a lot of work, very expensive to hire people to do this. They have to constantly crawl the internet. Google came up with a way for a computer to just crawl the internet and assign the page ranks automatically. What they said is, the computer will start anywhere on the internet at random, and then when you're on a page, there's a bunch of outlinks. You click one of them at random, you follow that one, and then you repeat this process. And as you repeat this, you're actually following a Markov model. There's a distribution over next states given current state, where state is the page that you're on, and next state would be one of the states that you can go to from that state. And there's a probability of getting reset, which actually helps with making sure there's a nice stationary distribution, so you don't have weird zero probabilities in certain states and so forth. So probability of being reset uniformly, but most of the time you just transition to an outlink page. Okay, so let's say you do that, and you follow this process, you look at the stationary distribution. Let's say you were to compute that, and that's exactly what Google did. They compute the stationary distribution. Then which pages will have a high probability to be on at time equal infinity? It's pages to which a lot of other pages link. But not just pages to which a lot of other pages link, also if a lot of pages link to a page that in turn links to you, that's also good for you. Some subtleties there, like it kind of might encourage you to not have any outlinks, so the random navigator gets stuck on your page, and there's fixes for that to make sure that you never just stay on a page. But so that's what they did. They computed the stationary distribution of this random web surfer Markov model, and that stationary distribution was then used to rank. So you would search, type in maybe 2 words, it would retrieve all the pages that have those words on them, and among those then show them in order of page rank. That's Google 1.0. That was so much better than anything else that everybody switched over to using Google rather than the other ones. And then the next thing happened, of course, is everybody uses it, but initially you still have to click maybe on result number 5 or result number 7. They log that clickstream data, they machine learn on top of their page rank, whatever else matters for you to select a particular page. And at that point, it's hard to catch up, because if you were to build Google 98, it won't be that great as Google today, and so you won't get the users, and so you won't get the ability to update how it ranks pages based on what users have done. But that was the foundation, and it was a lot better than anything people were able to do before. It might still be the best you can do if starting from scratch and having no user data of what users prefer. Any questions about this? You actually have seen a Markov model in one other place already too, in 188, which is Gibbs sampling. The star here means that this is kind of something a little advanced, and we don't expect you to necessarily fully follow along with what's happening here, but it's good to be aware of, and probably several of you will understand what's happening. So, let's say you do Gibbs sampling. What was Gibbs sampling? It's this process where you say, I have a basenet, I have a bunch of variables that are evidence variables, I have a bunch E1 through EM, I have a bunch of query variables, X1 through Xn, and I want to infer the distribution over the X variables, given the evidence variables. And let's say your basenet is big, and variable elimination doesn't work because you would need to generate a factor that's so big that you can't represent it on your computer, and it would take too long. Okay, you might run a sampling algorithm. Gibbs sampling is one of the most popular ones. In Gibbs sampling, you take a random instantiation of those X variables, then randomly pick one of them, and resample it conditioned on all the other variables. And sampling one variable in a basenet conditioned on all the others is actually a very efficient operation. So you do that operation, and then you randomly pick another variable, resample it conditioned on all the others, repeat, repeat, repeat. And it turns out if you keep doing this, the distribution over assignments of variables will converge to a stationary distribution. So just like in the weather Markov model, it was always either sunny or rainy. That was never at stake. It was either one or the other. It was never a combination. But the stationary distribution put 75% on sun, 25% on rain. Same thing will happen here. At any step in your process, all these variables have been assigned. Maybe it's plus x1, negative x2, plus x3, plus x4, negative x5, plus x6. But the distribution over what you end up with ends up being a stationary distribution that matches the correct posterior distribution of, not this one here. This conditional distribution is the stationary distribution of that process. Now, when you run this by sampling, you only get one sample of that distribution after you ran infinitely long. Then you repeat the process. You reinitialize everything, run that process again, get a second sample. Reinitialize, run it again, get a third sample, and so forth. And then the combination of samples together will reflect a stationary distribution, which you can then use to make some inferences from. So this star also means that, it's not expected that from this slide that you understand how the proof would work, but just want you to know that this is out there. Any questions about Markov models? The thing about Markov models is that in some sense, yes, they have some applications, but they don't really have that many applications. I mean, they have a roughly $1 trillion application, which is pretty good. But how about more applications? Typically, you need more than just a Markov models. You need something called a hidden Markov model. So, let's go back to this situation here. We watched me play this at the beginning of lecture, and honestly, it was pretty hard to play. But in principle, we should fuse the information we get from the readings down here to get an estimate of where the ghosts are. The ghost location is following a Markov model, but we're also having measurements. And these measurements we don't have in the Markov model. Once we have a hidden Markov model, we'll also have measurements. So let's take a look at that. So in a hidden Markov model, there's still a sequence of states shown here. That's not different. We've already covered that. That's the Markov model. But now in addition, we have observation, evidence variables at each time. For example, distance to each of the ghosts. In a hidden Markov model, we don't get to observe the hidden state, x1, x2, x3, x4, but the hope is that by observing the evidence variables, we can somehow infer a posterior distribution over the hidden states that allows us to do something interesting. Again, this is just a base net, right? If you look at this and you say we only have 4 time steps, so we cut it off right here, this is a base net. You have observed, let's say, E1 through E4. You can now run variable elimination or anything else that you like to run to infer the distribution over x1, x2, x3, x4. But what we're going to look at is something that over time keeps track of that distribution that's a little specific to HMMs, but if you think about it after the fact, you realize it's just variable elimination run from left to right. So here is a other example HMM. This is from the Russell and Norvig book. They call it the weather HMM, but if you hear the story, you would probably call it the sad grad student HMM. The story goes as follows. There's a grad student, but as it goes with very diligent grad students, they are just in the basement at all times. They don't come out of that basement. But luck has it, every now and then, professor stops by and says hi to them. And sometimes professor has an umbrella, sometimes not. And that, for the grad student, is a way to extract information about whether today might be a sunny day or a rainy day. Okay? I'm not saying this is realistic grad student life, but that's the story in the book. I hope it's not realistic. So that's what's going on here. Grad student really wants to know about the weather outside, doesn't get to look at it, but gets to see the professor carrying an umbrella or not. Now, there's multiple distributions involved. There's initial state distribution, initially sunny or rainy. There's a distribution for next state, like we saw in the Markov model, the transition model here. And then there's a distribution for evidence given current state. Okay, so let's put some numbers in. The transition model we've already seen before. Actually slightly different here, slightly simplified. It's made symmetric. Probability of rain on the next day, given rain on the previous day, is 0.7, and same the other way around. So it's 70% chance things stay the same, and 30% chance things switch up. Then, turns out, Professor, 90% of the time when it rains, Professor has an umbrella. And then when it doesn't rain, Professor still has an umbrella 20% of the time. So you can't just look at the umbrella or not to know where it's been raining. You need to do some probabilistic calculus to get a posterior over whether it might be raining or not outside. Not sure if it matters to know if you're always in the basement, but it's the calculation we're going to do. Okay, here's another example. Ghostbusters. So this is a smaller version of the grid that we looked at, just 3 by 3, uniform distribution initially. We have a transition model where they usually move clockwise in this grid, but might also veer randomly off that. And then there is a observation model where we have sensors that you also covered in last week's lecture, this Tuesday's lecture on value of perfect information, where the sensor could take on different colors depending on how far away the ghost is from where you made your measurement. And that's our observation, given state, conditional distribution. Okay, so let's take a look at the corresponding demo here. Okay, so we'll let time pass. Don't see anything happen because we hit the stationary distribution of the Markov model, but now we're going to consider it as a HMM, so we get a measurement. This time, this will change the distribution, then time passes again, we'll get another measurement, we'll change the distribution, time passes again, we'll get another measurement, maybe here, get another distribution, and so forth. So we have an alternation between time passes, which tends to diffuse where the ghost probability mass is, and then a measurement which tends to help us concentrate where the ghost might be. And that's the dynamics of an HMM. There's this alternation between time passing, a measurement, time passing, a measurement, and every step along that process, the distribution gets updated and hopefully gives us more and more concentrated information on where the ghost might be. Okay, so that's the HMM process in action. Let's think about the independence assumptions we make in this model. So the reason we talked about things like d-separation is such that when we look at a graph like this, we can just read off what is it that we're assuming by choosing this BaseNet graph. So what is it that we're assuming? Well, let's look at the hidden process. The hidden process up here, x1 through x4, what can we say about that? It's actually similar to what we had for the Markov model. It's still the case that if you know the state, let's say at time 3, knowing anything about the past before time 3 does not tell you anything about the future past time 3. So knowing the state at any given time separates past from future. How about if we have observations? What this model is saying is that if we know x3, the evidence we expect to observe, the distribution over evidence, is independent of anything else we could find out once we know x3. It's just x3 directly influences our measurement, and nothing else has any influence anymore. How about this question at the bottom here? Does this mean that evidence variables are guaranteed to be independent? Who thinks they're guaranteed to be independent? Who thinks they're not guaranteed to be independent? Let's see. Very few hands are going up. This is a question you should be able to answer. So either it's just so simple you feel offended you're even asked, or you need to do a little bit of review of this material. I'm not going to ask you which one it is. I'll just answer the question. So, are these evidence variables guaranteed to be independent? What's the question there? Well, let's look at some evidence variables. For example, E1 and E4. Are they guaranteed to be independent? Let's see. What paths do we have? This is a path, and it's actually the only path. Is that an active path or an inactive path? Well, let's take a look. The first triple here is active, second triple active, third triple active. All these triples are active because they're all, the first one is a common cause, and the next ones are causal chains, and nothing is observed in between because we said are they independent but not conditioned on anything? Are they just independent? So nothing's observed. So there is influence running. So indeed, we cannot claim this. So no. Answer is no. It changes, of course, if we were to observe, for example, x2, then all of a sudden we have independence here. We have E1 independent of E4 given x2. So those are the assumptions we're making. If you're not happy with those assumptions, you don't think they capture how the world works, well, then you should modify your model, because otherwise the conclusions from the model are not going to be very precise for what you're trying to do. Let's see. Let's take a short break here, and then let's do mini contest results and do the remainder of HMMs.
Do you have office hours next week, or is that then?
Oh. Okay, let's restart. Let's look at the mini contest 2 results. How did the game work? It was a game, each side controls multiple agents. Each agent is a ghost in their own territory, which they can then defend, and a Pacman on the other side, where they can go collect food pellets, but you only get points when you bring them back. If you get attacked by the opponent's ghost and eaten, then the food pellets respawn around you. So you win by returning all but 2 food dots. Well, you can all but 2, or it's fine if you return more and return all of them, but that's the minimum. All but 2 should be returned to win, or after 1,200 steps, if nobody has won yet, according to this rule, the game ends, and we just look at who has the most food pellets returned so far, so the running score. Many different layouts, so it's not about solving one particular scenario. The layouts are different in different games. How are the rankings calculated? For each of the 4 staff agents on the 6 different maps, 3 games per map are played. Then for each map, the score of the 3 games is averaged, and then the total score is the sum of all these average scores. There's also some extra credit involved on Project 2. If you were first place in the ranking, you get 2 extra credit points, second and third place 1.5, fourth to 10, 1 point, and 0.5 points for if you win at least 51% of the time against a baseline team we provided, similarly for the 3 staff agents. Okay, let's look at what happened. 35 participating teams, many interesting team names, which we always appreciate. Let's see. Team No Bug, Get Wrecked, My stupid code just cannot work. Please don't eat me. Then I'm going to read this as, please don't read me. I think it has a meaning. I looked it up yesterday, and I'm pretty sure it was not offensive, and it's okay to show in class, but I don't remember what it is. And then, actually, 3 dots isn't indicating there were more team names, but actually one of the team names was just 3 dots. Results. In 10th place, we had Wilson Wu, I would prefer not to, with 25 points. In 9th place, Victor Cheng, War of Greed. In 8th place, Ron Xie and Yuncheng Ma with Ruji. In 7th place, Jing Tan, Yitong Li with Team No Bug. In 6th place, Chang Yung Li, Find a Way. 5th place, Johannes Bommes with a unique leaderboard name. 4th place, Ariel Hirschberg with Waka X3. Congratulations, everyone in the top 10 listed so far. Then, in 3rd place, we have, don't forget, register to vote. If you want to get any message across in this class, your team name is your opportunity. The sole team member is Sean Liu. Who is Sean? Is Sean here? Can you raise your hand if you're here, Sean? Oh, you have 2 people. Oh, what's your name? Adam? H.M. Ham. We'll see more Ham in one of the future lectures, actually. Ham and Sean, congratulations. So, score of 99. Apologies for no Ham on the slide. Somehow, clicking on Gradescope did not show your name as a partner, so we might have to do some fixing so you get the extra credit points. Bot description. Minimax with the offensive agent looking at score, distance to ghost, distance to home, distance to pallets, number of pallets left, number of power pallets left. When the enemy is 2 away, encourage to go home, otherwise encourage to collect more food. So you can reweight those features in different ways depending on which situation you're in. The defensive agent is measuring distance to enemy Pacman and trying to get as close as possible. Then the defensive agent plays a trick. It flaunts and dances near the border to lure you in. So sometimes at the border, these things get stationary and don't move, but this agent will, dance and flaunt, whatever that means exactly, and you will come closer and be eaten. This is what it looks like in action. So this is against one of the staff agents. On the left, in red, is the 3rd place team. Don't forget, register to vote. Working their way. And on the right is the staff team, also trying to work their way, though maybe one of the ghosts not working their way that much. So the score is still 0, even though food pallets have been eaten, because nobody's brought food pallets back yet. So red is up by 2. So red is still up by 2. Oh, it succeeded. It lured in the staff agents and ate them. Time to go back. Bring back a lot of food pellets. Score 6 now. Playing more games. Let's fast forward this a little bit if we can. So Team Red wins this one. Let's move to the next one. Second place is YZY, Yuchen Wu, and Yuzi Shu. Are Yuchen and Yuzi here? Both here. Congratulations. You run a search, and I'll play this in parallel to explaining. If the closest ghost is near, alpha beta is run for 2 turns. If the closest ghost is not near, this is when you're an offensive agent, greedy tree search to just cover as many food pallets as quickly as possible. Evaluation functions had a lot of sophisticated features, more than I could put on this slide. Also pay attention to dead ends, very specifically, because of course you don't want to get trapped. And then more emphasis on Y coordinate than X, because Y is often the way you can keep people blocked, whereas X doesn't play as big a role in that. See this agent in action. Also beat staff agent. I'm going to move forward through this one to first place. First place is @_@ Philip Zhao and Winnie Gao. Are you here? Philip, Winnie, over there. Congratulations. So let me play this one while we explain. If there are no opponents on their side, both agents are offensive. When opponents enter their side, one of the agents will turn defensive. Often the closer agent, the defensive agent, works similar to the baseline defensive agent. During initialization, the dead ends in the map are found and blocks in the dead alley are assigned a danger coefficient, which is the number of steps required to escape. This danger coefficient plays an important role in the evaluation function, and the offensive agent runs a minimax of depth 1. Let's see this in action here. Zero food pallets left on the other side. Okay, so HMMs. This is the basenet model corresponding to it. What are some real HMM examples? Well, speech recognition. The observed variables are the sequence of numbers corresponding to the pressure that you observe in the air coming at you. And the unobserved variables are the characters or the phonemes or the words, whichever version of transcription you're using. Machine translation. The observed evidence is words or characters or symbols in one language. The unobserved is characters, symbols, or words in the other language. Robot tracking. Observations could be sensory readings, like laser rangefinder readings, and the unobserved is the state, the localization of the robot. Filtering and monitoring is the process of tracking the distribution over state-given evidence. So keeping track of this belief state, that's why it's called B, belief state over state, which is a conditional of state at a time xt given all evidence up to time t. We will start with belief state at time 1, usually uniform, and then as time passes, or we get observations, we update the belief. The Kalman filter hash is an example of an HMM that happens to use continuous variables, which we're not going to do, but was used in the Apollo project and critical to getting to the moon. So, what's an example of this in action for robot localization? This robot could be anywhere in this grid, so everything's equally gray. The observation model is that it senses to the top, the bottom, left, right. It senses whether there's a wall or not. It makes at most one error. So when it's there, it could have 5 different types of readings. The reading where there is no error, or the other 4 readings where you make one error in your 4 readings. That also means that when you read something, you can't count on it being an exact match to where you are. So at time 0, we have a uniform distribution over wherever the robot could be. Then the robot will move. We know the action of the robot, so we can do a next state calculation. Actually, will this robot move? Yeah, it'll move. So we'd first do a sensory reading. We do a belief update based on the sensory reading. We read wall top, wall bottom. This is now our posterior. Then the robot will move to the right. We'll have a transition model for that. It's not guaranteed to move one to the right, but with high probability it will. Then we get another sensory reading. We see wall top, wall bottom. We're showing it here, and that's because we know it's there because we're kind of looking from above and knowing how the world works. But the HMM itself doesn't know where the robot is. It has a distribution over where the robot might be. Then moves again, also does a sensory update, and keeps repeating this. And then when it's here, symmetry gets broken. It knows it's in the top hallway, not the bottom hallway, not for sure, but very likely, and knows itself, its localization pretty well. Okay, so what are the base cases? We either observe evidence, which is we want to then compute the posterior of x1 given the evidence E1. How do we do this? Well, this is the calculation. What's happening here? The conditional of x1 given E1 is by definition the joint of x1 and E1 divided by the probability of E1. Then we use this sign over here, saying we're now going to get rid of this thing over here by using this sign. It's kind of weird, but it's just saying we're interested in the distribution over x1. So our variable is x1. E1 is not a variable. Only x1 is the variable. So anything that does not involve x1, we can just remove if it's just multiplied in, and here it's divided in, that's the same as multiply. We can just remove it and say it's proportional to this. And then we can fill in the model and get this thing over here. What would be the result of this calculation? We would have a table for values of x1. We would then have values that are proportional to x1 given E1. And maybe it would look something like this. x1 could be 0 or 1, and then proportional says 0.2 on this and 0.3 on this. If you want them to know the actual probabilities, you will say, oh, well, that's only proportional. I now need to renormalize, so it'll be 0.2 over the sum of those and 0.3 over the sum of those again. That will be the actual probability. So that's what's happening over here. We got rid of this thing, which happens to be corresponding to the sum of those. This is often done because it's easier to just get rid of things that don't really matter if you know all you need to do at the end is just renormalize to get the correct probabilities. Okay, so that's computing the conditional of x1 when new evidence comes in. Then the other thing that can happen is a transition over time. This is the Markov model update. We've seen this before. This is just the joint between x1 and x2, summing out over x1, which is this thing over here. And that's exactly what we've been doing in the first half of lecture. Okay, so let's now make this a little more explicit. These are the base cases. These are very simple base nets with only 2 variables. Can we now use this in a HMM where this process repeats over and over and over? Well, let's see. We want to believe a time t, which is conditional of xt given all past evidence. After one time step passes, we now want to transition to xt plus 1 given e1 through t. This notation here means we're conditioning on all evidence variables from e1 all the way through et. It's just a shorthand for many, many evidence variables all the way from 1 through t. Okay, well, what is it other than sum? We can bring in an extra variable and sum it out. You can always do that with a distribution over one variable, bring in another one, and just sum it out. The reason we bring in xt is because we assume recursively that we already know the belief for time t. So by bringing in xt, we might be able to build on something we already have. Whereas for xt plus 1, we don't have the answer yet. So we bring in xt, we sum over it. We can now use the dynamics model say that, okay, this joint is the conditional here times the distribution for xt given all evidence. This is exactly what a dynamics model looks like, except that everywhere we have the additional conditioning on E1 through ET. That's the only thing we added in. Otherwise, this is just a dynamics model update. Now, we don't have all of these available. The red one we already have available. The black one we don't. What do we need to do? We need to somehow make an assumption. The hidden Markov model gives us the assumption that this thing here does not depend on these variables. The distribution over xt plus 1 is given xt, doesn't depend on the evidence, so we can get rid of that. Now we have quantities we know. This one we know recursively from the previous computation. This one is in our dynamics model, and we have the ability to compute, maybe in compact notation, the belief at the next time. So it is exactly the Markov model calculation done again. We're just conditioning on E1 through ET everywhere, and the place where our assumption comes in, the one place where we make an assumption in this entire calculation is when we get rid of this conditioning here. This here is something we can always do. It does not depend on the structure of our BaseNet or HMM, but this transition here, getting rid of this, that's using a very specific conditional independence assumption that we have in this model. Okay? So we see that beliefs essentially just get pushed through the transition model, get the beliefs for the next time. Often, what it means is that uncertainty will accumulate. We've seen this with the ghost environments. As we push through the transition model, the ghost will kind of circle around, but also diffuse their probability, and it'll take measurements to concentrate that distribution again. So, we've seen this in demo. How about the observation? We want to know the belief after an observation. So we assume we already have the belief before an observation. So this is, assume we know that recursively from the previous calculation. Can we use this to now get the distribution for xt plus 1 given all evidence up to time t plus 1? This is only up to time t. Okay, well, how do we do that? To be able to condition on also evidence at time t plus 1, this is what we need. And we somehow need to get this in terms of this expression we already have and our measurement model, the distribution over et plus 1 given xt plus 1. Because that's going to tell us how the evidence influences our belief. Okay, well, we know that we can expand this by definition this way. And notice that again, E1 through T are just kind of hanging off the back. If they weren't there, this would look a lot simpler to you, but of course we need them there to be complete here. Then we do the proportional thing. What does that mean again? Well, we're interested in the distribution over xt plus 1. That's the only variable. This stuff in the back here doesn't have xt plus 1 in it. It's a constant as far as xt plus 1 is concerned, so you can remove it. Note that it needs to be a multiplication with a constant. If it's a plus some constant, you can't just drop it. But if you multiply with a constant, you can drop it and later renormalize. Okay, then we can use, and again, imagine these are not here for a moment, then this should look very simple to you. It's just decomposing the joint over two variables in the marginal plus the conditional, and then just everywhere we also condition on all those past evidence variables. Then we apply an assumption. Getting rid of this thing over here is saying that the evidence at time t plus 1 does not depend on any past evidence if we know the state at time t plus 1. That's an assumption. This here is where our assumption comes in. Now we have it expressed in terms of what we already had and something that's in our model, our measurement model, and we can do this calculation. What will be the result of this calculation? It will be something that's proportional to what we care about, and then we can just renormalize, which means we'll have a table with a bunch of entries. They won't sum to 1, but we'll sum them up nevertheless. We'll see it's not 1, and then we'll divide every entry by the sum to get it to sum to 1. And what we're doing in that process, effectively, we're computing this thing over here, which we kind of decided to forget about, and by summing all the entries, we get this thing over here, and then we divide by it to get things to sum to 1. Okay, or more compactly, we have that the belief at the next time is proportional to belief at the previous time multiplied with probability of evidence. So if the evidence is very compatible with the next state, then the probability mass will go up for that next state. If the evidence is very incompatible with the next state, the probability mass will go down for that state. That's the multiplicative effect happening over here. Okay. So typically, when an observation happens, beliefs will concentrate, as we see going from left to right here. Let's look at the weather HMM. This slide is working through the math. We start with a uniform distribution over here. Then we transition to again uniform, because just the way the transition model is set up. But then we have an observation which sees plus R, which then moves more weight onto, or we see an umbrella, which is correlated with plus R, and so we see more mass shifted onto the plus R, and then this process repeats. These are the numbers corresponding to these tables over there. If you work through the equations on the previous slide, you then get these numbers here. And it's just a very procedural thing you can just repeat over and over to get the conditional distribution of current state given all past evidence. There's another way to write this. Another way to write this is in one big update. So rather than saying I'm doing a time update and I'm doing a evidence update, I'm going to just do one update. So how would that work? Let's say I want this quantity as a function of that quantity at the previous time. I'm first going to say, well, really I should be dividing here by E1 through T. But that doesn't depend on xt, so I'm just using this proportional sign here to get rid of that division, and we can later make things sum to 1, and that will make up for this. Then I can write this out as bringing in xt minus 1. Why? Because we want a recursive update equation as a function of what we had at the previous time. So we bring in xt minus 1 and sum it out. Then we can decompose this into what we already have, thing for xt minus 1, then the transition model and the evidence. So we have both things happening at the same time here, transition and evidence. We can reorganize this a little bit, and this would be the kind of single update way of getting both the transition incorporated and evidence. It comes down to the same result as doing it one and then the other, but sometimes this might be convenient to do it this way. If you look at the details, you'll see that if you do variable elimination, and you eliminate variable x1, then x2, then x3, then x4, all the way to xt minus 1, and you end up with a distribution for xt, given all past evidence. It's exactly the same as this calculation here. As long as you do your variable elimination, going from time 1 all the way to the time you're currently at. Online belief updates, which is most common, is where you would essentially just do these things. So you would update for time, which we derived is this equation. Then you'd update for evidence and repeat. If you have multiple time updates without evidence, then you just repeat this one multiple times. And then once finally some evidence comes in again, you can do an evidence update. Now, keep in mind again, this thing here means this is an unnormalized update. It will be an unnormalized distribution, which you need to normalize by summing all the entries and dividing by every entry by the sum. Okay, once we do this, we can reconsider the Pacman game that we saw at the very beginning. And we can have an agent play it with beliefs visualized. So it's showing in color the distribution over possible locations of each of the ghosts. And then, of course, you can run a search to try to get as close as possible to the ghost, because you're more powerful than the ghost in this game, and go put it in its ghost jail slot at the bottom left. And if your project 4 is successful, this is pretty much what it should look like when fully up and running. Difficult one? Ghost is escaping, it seems. Oh, come on, random seed. Give Pacman a break. Okay. That kind of showcases that, it's not always the ghost is where the maximum probability is. It might very well be at one of the low probability squares. So, let's see. What's left for us? Next time, we'll look at particle filtering and more applications of HMMs. What particle filtering will do will be the counterpart of sampling methods that we saw in Bayesian networks, but then sampling methods for HMMs. This is for when your HMM has too large a state space to be able to run the algorithms we saw today. All right?